Welcome to today's problem walkthrough. We're diving into LeetCode problem number 1514, path with maximum probability. In this problem, we'll explore how to find the most reliable path between nodes in a graph, where edges represent probabilities. Let's get started. In this problem, we are working with an undirected graph that consists of n nodes, numbered from 0 to n1. The graph is defined by an edges array, where each entry specifies a connection between two nodes, and a corresponding subprob array that assigns a success probability to each edge. The task is to determine the maximum probability of successfully traveling from a given start node to a specified end node. If no such path exists, the result should be 0. The input includes the number of nodes, the list of edges, their success probabilities, and the start and end nodes. The output is a single floating point number representing the maximum probability, with a precision requirement of up to 10^-5. To better understand the problem, let's consider the first example. Here, we have n equals 3 nodes and 3 edges, 0, 1, 1, 2, and 0, 2, with respective success probabilities of 0.5, 0.5, and 0.2. The starting node is 0, and the destination node is 2. There are two possible paths to reach the destination. The direct path 0-2 has a success probability of 0.2. The other path is 0-1-2, where the total probability is calculated as 0.5 * 0.5 equals 0.25. Since the second path has a higher success probability, the output for this example is 0.25. Now let's look at another example. Here, the graph structure remains the same, but the success probabilities are slightly different, 0.5, 0.5, and 0.3. Once again, there are two paths from node 0 to node 2. The direct path 0-2 now has a success probability of 0.3, while the indirect path 0-1-2 has a probability of 0.5 * 0.5 equals 0.25. This time, the direct path provides the higher probability, so the solution to this example is 0.3. In the third example, the graph is much simpler. We only have one edge, 0, 1, with a success probability of 0.5. The task is to find the maximum probability of traveling from node 0 to node 2. However, there is no edge connecting 0 to 2, either directly or indirectly. Since no path exists between the start and end nodes, the output is 0. This highlights an important case where a disconnected graph results in no valid solution. Finally, let's review the constraints and edge cases. The graph has between 2 and 10^4 nodes, and the number of edges can go up to 2 * 10^4. Each edge connects two distinct nodes, and the success probabilities for edges range from 0 to 1. Self-loops, where a node connects to itself, are not allowed. For edge cases, consider scenarios like graphs with no edges, which yield 0 unless the start and end nodes are the same. Disconnected graphs also result in 0 when no path exists. The algorithm must handle large graph sizes efficiently and ensure high precision in the output, with an absolute error less than 10^-5. Additionally, if multiple paths yield the same maximum probability, the solution must account for all paths and return the correct result. To approach this problem, we first consider a brute force method. The intuition here is straightforward: enumerate all possible paths between the start and end nodes, calculate the product of probabilities for each path, and choose the one with the highest probability. This can be implemented using backtracking or a depth-first search approach. However, computing all possible paths in a graph quickly becomes computationally expensive, as the number of paths grows exponentially with the size of the graph. This results in a time complexity of O(2 to the power of n) in the worst case. Additionally, storing all paths can lead to significant memory overhead. While this approach is conceptually simple, it's impractical for larger graphs due to the sheer number of combinations and the resources required to evaluate them. To address the inefficiencies of the brute force approach, we turn to a modified version of Dijkstra's algorithm. The key idea here is to maximize the probability of success along the path, rather than minimizing distance as in the standard version. By leveraging a max heap, we can prioritize paths with the highest probabilities during exploration. In this method, we represent the graph as an adjacency list, where each edge stores its associated probability. Starting from the source node, the algorithm iteratively explores the most promising path first, updating the probability of reaching each node when a better path is found. This process continues until the destination is reached or all possible paths are exhausted. The time complexity of this approach is O(E) log v, which is efficient for sparse graphs, as it depends on the number of edges and vertices. One thing to keep in mind is that this approach relies on floating point calculations, which could introduce minor numerical inaccuracies, but these are generally negligible in competitive programming. Another option to solve this problem is the Bellman-Ford algorithm, which uses dynamic programming instead of a priority queue to find the maximum probability path. Starting with a probability of 1.0 at the source, the algorithm iteratively relaxes all edges, updating the probabilities of reaching other nodes. This process is repeated for at most n1 iterations, where n is the number of vertices. Bellman-Ford has a time complexity of O(V*E), which can be less efficient than Dijkstra's algorithm in sparse graphs but may perform better in dense graphs. While it's conceptually simpler and avoids the need for a max heap, the slower runtime for large, sparse graphs makes it less appealing. Ultimately, we choose the modified Dijkstra's algorithm as the preferred strategy because it provides the best balance of efficiency and simplicity for this problem. The key insight here is leveraging the multiplicative nature of probabilities and using a max heap to prioritize the most promising paths. Like any algorithm, the modified Dijkstra's approach comes with trade-offs. One consideration is precision. Since it relies on floating point arithmetic, small numerical inaccuracies could arise, though these are typically acceptable within the context of competitive programming. Another factor is graph sparsity. This approach is highly optimized for sparse graphs, where the number of edges is significantly smaller than the square of the number of vertices. For dense graphs, where edges are abundant, the Bellman-Ford algorithm might be a better fit despite its higher theoretical complexity. In conclusion, the modified Dijkstra's algorithm stands out as the most practical and scalable solution for solving the path with maximum probability problem. Its ability to efficiently prioritize paths and handle sparse graphs makes it the ideal choice for this scenario. To solve the problem of finding the path with the maximum probability between two nodes in a graph, we start by representing the graph as an adjacency list. This means each node is a key in a dictionary, and its value is a list of tuples representing its neighbors and the probabilities of the edges connecting them. For example, if there's an edge between nodes U and V with a probability P, we include VP in U's list and UP in V's list. This bidirectional representation ensures that we can traverse the graph efficiently in either direction. Using an adjacency list is both memory efficient and allows quick access to a node's neighbors, which is crucial for our algorithm. Next, we use a max heap to prioritize the paths with the highest probabilities. Since Python's heap is a min heap by default, we store negative probabilities to simulate a max heap. We initialize the heap with the start node and a probability of 1, represented as -1, start_node. The negative sign allows us to prioritize the largest probabilities when extracting from the heap. This approach ensures that at each step, we are always working with the most promising path available. Now, we need to track the highest probability of reaching each node during our traversal. For this, we use a dictionary called max_prob, where the keys are the nodes and the values are their respective maximum probabilities. Initially, all nodes are set to 0, except for the start node, which is set to 1, since we begin there with full certainty. This dictionary helps us avoid revisiting nodes with lower probabilities, saving computational effort. Next, we process the heap until it's empty. At each step, we extract the entry with the highest priority, which corresponds to the highest probability path. If the current node is the target node, we return its probability, converting it back to positive since we stored it as negative. For each neighbor of the current node, we calculate the new probability as the product of the current probability and the edge probability. If this new probability is greater than the one currently recorded in max_prob, we update the dictionary and push the neighbor onto the heap with the updated probability. This ensures that only the most promising paths are pursued further. Finally, if the heap is exhausted and the target node hasn't been reached, we return 0, indicating that no valid path exists. This ensures our algorithm handles disconnected graphs or unreachable targets gracefully. The algorithm leverages a greedy approach by using a max heap to ensure that the most promising path is always expanded first. This makes the solution both efficient and optimal for this problem. By maintaining the max_prob dictionary, we avoid redundant computations, as we don't revisit nodes with probabilities lower than the maximum already recorded. This significantly reduces unnecessary work, making the algorithm efficient in practice. The approach also gracefully handles edge cases, such as disconnected graphs where the output is 0 if the target is unreachable, and self-loops, which are ignored unless they contribute to a valid path. The key data structures used are the adjacency list for efficient graph representation, the max heap for prioritizing paths by descending probability, and the max_prob dictionary for tracking the maximum probability of reaching each node. The algorithm's time complexity is O, E * log, V, where E is the number of edges and V is the number of nodes. Each edge is processed once, and heap operations require O, log, V, time. The space complexity is O, V plus E, accounting for the adjacency list and auxiliary data structures, making this approach both time and space efficient. Let's walk through an example to see the algorithm in action. Consider a graph with nodes A, B, and C, and edges with probabilities as follows: A, B, 0.5, B, C, 0.6, and A, C, 0.2. The start node is A, and the target node is C. First, we build the adjacency list. A maps to B, 0.5, C, 0.2, B maps to A, 0.5, C, 0.6, and C maps to A, 0.2, B, 0.6. Next, we initialize the max heap with -1, A, and the max_prob dictionary with A, 1, B, 0, C, 0. We begin by popping -1, A, from the heap. From A, we calculate new probabilities for its neighbors. For B, the probability is 1 times 0.5 equals 0.5, so we update max_prob for B and push -0.5, B, onto the heap. For C, the probability is 1 times 0.2 equals 0.2, so we update max_prob for C and push -0.2, C. Next, we pop -0.5, B, from the heap. From B, the probability to reach C is 0.5 times 0.6 equals 0.3. Since 0.3 is greater than the current max_prob value for C, we update it and push -0.3, C, onto the heap. Finally, we pop -0.3, C, and return 0.3, which is the highest probability path from A to C. This step-by-step process demonstrates how the algorithm efficiently finds the optimal path. To solve this problem, we start by importing the necessary library, heap, which we'll use for our priority queue. Then, we define the max probability function, which takes the number of nodes n, a list of edges, their success probabilities sucprob, and the start and end nodes as inputs. First, we construct the graph as an adjacency list. Each node maps to a list of its neighbors, where each neighbor is paired with the corresponding success probability. This allows us to represent the undirected graph efficiently. After building the graph, we initialize a priority queue with the start node and a probability of 1.0, stored as -1.0 because Python's heap is a min heap by default, and we need to simulate a max heap. We also initialize an array, max_prob, to track the highest probability of reaching each node, setting the start node's probability to 1.0. The main processing happens in the while loop, where we repeatedly extract the node with the highest probability from the queue. Inside the loop, we negate the stored probability back to its positive value. If we reach the target node, we return the current probability immediately. Otherwise, we iterate through the node's neighbors to explore potential paths. For each neighbor, we calculate the new probability of reaching it by multiplying the current probability with the edge probability. If this new probability is greater than the previously recorded probability for the neighbor, we update it in the max_prob array and push the neighbor into the priority queue with the updated probability, negated to maintain the max heap behavior. This ensures that we always prioritize nodes with higher probabilities as we continue exploring the graph. Finally, after the loop, if the end node is not reachable from the start node, we return 0.0 as the result. This implementation ensures an efficient solution using Dijkstra-like logic tailored for probabilities instead of distances, and the use of a priority queue keeps the time complexity manageable even for larger graphs. To solve this problem, we start by building the graph as an adjacency list. Each node in the graph is associated with a list of pairs, where each pair represents a neighboring node and the probability of successfully traveling to it. We initialize the graph with empty lists for all nodes, and then populate it by iterating through the edges. For each edge, we add both directions to ensure that the graph is undirected. Next, we prepare a priority queue to help us process nodes in order of their maximum probability. This queue stores pairs of nodes and their respective probabilities, and we configure it to behave like a max heap by comparing probabilities in descending order. We also initialize an array to keep track of the maximum probability to reach each node, setting the start node's probability to 1.0 because we begin there with full certainty. The while loop then begins, which continues processing nodes until the queue is empty. Inside the while loop, we process the node with the highest probability by removing it from the priority queue. If this node is the target, we return the probability immediately, as we've found the best possible path. Otherwise, we iterate through its neighbors. For each neighbor, we calculate the new probability of reaching that node by multiplying the current probability with the edge probability. If this new probability is higher than the previously recorded probability for this neighbor, we update the maximum probability and add the neighbor to the priority queue with its new probability. This ensures that we prioritize processing nodes that offer a higher probability of reaching the target. The loop continues until all reachable nodes are processed, or we find the target. Finally, if we exhaust the priority queue without reaching the target node, we return 0.0, indicating that the target is not reachable. To support this implementation, we define a helper class called pair, which encapsulates a node and its associated probability. This class has a simple constructor that initializes these two fields. The pair class is used extensively throughout the code to represent the relationships between nodes and their travel probabilities, both in the graph and in the priority queue. With this structure, the algorithm efficiently calculates the path with the maximum probability using a combination of Dijkstra's algorithm principles and a max heap. To solve this problem, we start by constructing the graph based on the given edges and success probabilities. The graph is represented as an adjacency list, where each node maps to a list of tuples representing its neighbors and the probability of successfully traveling to them. For example, the edge between nodes 0 and 1 with a success probability of 0.5 is added as 1, 0.5 to graph 0 and 0, 0.5 to graph 1. Similarly, we process the edges between nodes 1 and 2, and nodes 0 and 2. Once all edges are processed, the graph structure is complete, and we can see that each node has its corresponding neighbors and probabilities stored. Next, we initialize the priority queue with the starting node, setting its probability to 1.0 since we are certain of being at the start. We also initialize a list to track the maximum probability to reach each node, setting the start node's probability to 1.0 and all others to 0.0, as they are initially unreachable. Starting the first iteration, we extract the node with the highest current probability from the priority queue, which is node 0 with a probability of 1.0. For each neighbor of node 0, we calculate the new probability of reaching that neighbor by multiplying the current probability with the edge's success probability. For neighbor 1, this results in a new probability of 0.5, which is greater than the current maximum probability for node 1. We update max_prob 1 to 0.5 and push the updated probability along with the node into the priority queue. Similarly, for neighbor 2, the new probability is 0.2, which is also greater than its current maximum probability. We update max_prob 2 to 0.2 and push it into the queue. At the end of this step, the priority queue contains nodes 1 and 2 with their respective probabilities, and the max_prob list reflects the updated probabilities. In the second iteration, we process node 1, which is now the highest priority node with a probability of 0.5. Again, we traverse its neighbors, calculating new probabilities. For neighbor 0, the calculated probability of 0.25 is less than its current maximum, so we skip it. For neighbor 2, the new probability of 0.25 is greater than its current value, so we update max_prob 2 and push the updated probability into the queue. The updated priority queue and max_prob list reflect these changes. In the third iteration, we extract node 2 from the priority queue with its highest probability of 0.25. Since node 2 is our target node, we can immediately return the current probability of 0.25 as the result. This means the maximum probability of successfully traveling from node 0 to node 2 is 0.25. This concludes the first example. Now, for the disconnected graph example, we start by constructing the graph. Here, node 3 remains disconnected as it has no edges. After initializing the priority queue with the starting node and setting its probability to 1.0, and initializing the max_prob list, we are ready to perform the iterations. In the first iteration for the disconnected graph, we process node 0 with a probability of 1.0. Traversing its neighbors, we calculate the probability to reach node 1 as 0.5. Since this is greater than the current maximum probability for node 1, we update max_prob 1 and push the updated probability into the priority queue. The updated max_prob list and priority queue reflect these changes. Moving to the second iteration, we now process node 1, which has the highest probability of 0.5. Calculating the probability to reach its neighbors, we find that the probability to reach node 0 is less than its current maximum, so we skip it. For neighbor 2, the new probability of 0.25 is greater than its current value, so we update max_prob 2 and push it into the queue. The priority queue now contains node 2, and the max_prob list is updated accordingly. In the third iteration, we process node 2 with its highest probability of 0.25. Traversing its neighbors, we see that the calculated probability to reach node 1 is less than its current maximum, so we skip it. With no more updates to the priority queue, the queue becomes empty. Since the target node, node 3, remains unreachable, we return a probability of 0.0. This concludes the second example. In the third example, we have a single node where the start and end nodes are the same. For the single node example, the graph construction step results in an empty adjacency list for the node, as there are no edges. The priority queue is initialized with the single node, and its probability is set to 1.0 in the max_prob list. In the first iteration, we process the node with its probability of 1.0. Since the current node is the target node, we immediately return the probability of 1.0. This indicates that the maximum probability of successfully traveling from the start node to the end node in this case is 1.0. This concludes the walkthrough of the solution. To analyze the time complexity, we begin with graph construction. The graph is represented using an adjacency list, which is built by iterating through the list of edges. Since there are m edges in the graph, this step takes m time. Next, we consider the priority queue operations. Here, we use a min heap, implemented with heap, to store nodes along with their probabilities. For each edge during traversal, we perform heap push or heap pop operations. Each of these operations has a logarithmic complexity of O log k, where k is the current size of the heap. In the worst case, every edge is processed once, leading to a total time complexity of O m*log n for the heap operations. Together, these steps form the basis for understanding how efficiently the algorithm handles graph construction and priority queue manipulation. Now, let's consider the graph traversal stage. Here, we visit each node's neighbors, which is proportional to the total number of edges in the graph, m, since the graph is represented as an adjacency list. This traversal step adds m to the overall time complexity. When we combine graph construction, priority queue operations, and traversal, the total time complexity becomes m plus m*log n. Since the graph traversal and heap operations dominate, the overall time complexity simplifies to m*log n. Shifting to space complexity, the adjacency list representation requires space proportional to the number of edges, m, because each edge is stored twice, once for each direction. This contributes m to the total space usage. Additionally, the priority queue itself can hold up to n nodes at any given time, where n is the number of nodes in the graph. This means the heap requires n space. Another component contributing to the space complexity is the max_prob array, which stores the maximum probability for each node. Since there are n nodes, this array also requires n space. Combining these factors, the total space complexity is m plus n. For best, average, and worst-case scenarios, the algorithm performs differently. In the best case, where the start node is the same as the end node, the algorithm finishes after one heap operation, in O1 time. In an average case, it processes only a subset of nodes and edges, with complexity dominated by graph traversal and heap updates, resulting in M*log n. In the worst case, all M edges and end nodes are processed, leading to the full complexity of M*log n. When comparing approaches, a naive method would involve exploring all possible paths between the start and end nodes to calculate their probabilities. This approach is highly inefficient, as it requires checking an exponential number of paths in the worst case, making it impractical for large graphs. In contrast, the optimized algorithm uses a Dijkstra-like strategy with a priority queue to explore only the most promising paths. While the heap operations introduce a logarithmic overhead, this is a significant improvement over the brute force approach. To summarize, the overall time complexity is M*log n, and the space complexity is M plus n. This efficiency stems from the algorithm's ability to process all edges and nodes using the adjacency list and priority queue, while the supporting data structures ensure minimal additional space usage. When solving this problem, there are common mistakes that can trip you up if you're not careful. First, overlooking edge cases can lead to unforeseen errors. For example, if the graph is disconnected, there may be nodes with zero probabilities or paths that form a cycle back to the start. Such scenarios can result in infinite loops or incorrect calculations, so it's essential to test your solution with both minimal and extreme inputs. Another common issue is misinterpreting how probabilities are calculated. Remember, probabilities multiply across edges rather than add. Summing them will produce invalid results. Efficiency is another critical factor. Using brute force to explore all possible paths might seem straightforward, but it's computationally expensive, especially for large graphs. To avoid this, you should prune low probability paths early. Additionally, be cautious when implementing a greedy approach, such as one inspired by Dijkstra's algorithm. If you're simulating a max heap with a priority queue, ensure that probabilities are negated correctly to maintain proper prioritization. Lastly, watch out for floating point precision errors when dealing with very small probabilities, as cumulative inaccuracies can distort your results. Using a tolerance threshold can help mitigate these issues and maintain accuracy. Now, let's consider some key insights for interviews. This problem primarily revolves around navigating a graph where the weights represent probabilities, so it's vital to have a strong grasp of graph traversal techniques like DFS, BFS, and Dijkstra's algorithm. Interviewers often expect you to optimize your solution using a greedy approach, where priority queues are used to prioritize paths with the highest probability. Make sure you understand the trade-offs involved. While brute force explores all possible paths, it's computationally expensive. Greedy algorithms or dynamic programming methods typically achieve better time complexity, often around E*log v, when using priority queues. During interviews, it's also important to clearly articulate how you handle edge cases. For instance, you should be able to explain how your solution deals with unreachable nodes or cycles in the graph. Lastly, it's helpful to draw connections to similar problems, such as LeetCode 743, which focuses on network delay time, or LeetCode 787, which involves finding the cheapest flights within a limited number of stops. By practicing these related problems, you can refine your understanding of graph-based algorithms and their variations. Finally, let's explore some alternative approaches and the trade-offs they involve. A brute force method would involve exploring all possible paths, calculating their probabilities, and selecting the maximum. While this guarantees correctness, it comes at the cost of exponential time complexity, which is impractical for large graphs. A more refined approach is using DFS combined with memoization to store intermediate results. This reduces redundant calculations and improves efficiency, but it may still struggle with scalability on very large graphs. The most efficient approach is often Dijkstra's algorithm, where a priority queue is used to greedily explore paths with the highest probability first. This method achieves a time complexity of E*log v, and is well suited for this type of problem, though it does require careful management of the priority queue. Another option is the Bellman-Ford algorithm, which is useful for graphs with negative weights. However, it's generally less efficient for this problem, with a time complexity of V*E. Understanding these trade-offs allows you to select the best approach based on the graph's size and constraints. Great job finishing this problem. We reviewed the path with maximum probability and discussed how to adapt Dijkstra's algorithm for probability-based graph traversal. Remember, mastering these algorithms will help you tackle a wide range of graph-related problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!